Hello everyone. I hope everyone has entered the. Has everyone entered? Will I leave? Will I? Yes, yes, yes. Okay. I'm locking the meeting then. Okay. Okay. No more participants. Okay. Fine. So we will begin with kinetic theory of gas, and this is one of the major chapters of this semester. So it's a very nice thing to know. We'll begin with kinetic theory of matter. It actually gives us an explanation to the nature of motion of molecules and the nature of heat energy. And according to this theory of matter, every substance, whether it's in the form of solid, liquid, or gas, consists of very large number of small particles that is known as the molecules. And the study of this kinetic theory, which is a microscopic theory, is best made through a study of gases. In the case of solid and liquids, it is comparatively less developed and valid only in limited senses. So in what follows is that the study of gases that we shall be mostly confining our studies to. And most important fact is that the kinetic theory of matter depends upon two fundamental hypotheses: the molecular constitution of matter, and the next one is the identification of heat with the motion of the molecules. Okay, so the first thing that before starting the kinetic theory of gases, the most important thing is that we should be dealing with is the kinetic model. Okay, so what is kinetic model? Okay, so we will be learning about kinetic model. So the kinetic model actually gives you some idea about the kinetic theory of gases. The properties of gases can be explained on the basis of this kinetic model of gas. And according to this model, every gas is made up of minute particles, and these are called the molecules. So the kinetic model gives us the concept of molecules, which are minute particles. Okay, and all molecules of the pure gas are identical. So this is a very important fact that the molecules of the gas are all identical, and the molecules of the gas are moving in all directions. So they move in all directions and with all possible velocities. Moves in all direction and with all possible velocities. Please pardon my handwriting. I'm just trying to give you the idea via using this virtual board, because we are not having regular classes in college. I don't know when it will reopen. So just try to get some idea from this. Okay. So so the things that we have just covered up is that the kinetic model gives us an idea about the molecules, which are very minute particles, and they all are identical and they move in all directions with all possible velocities. Hence, this fact gives us the idea that the motion is actually a haphazard motion. Okay. Okay, it's a haphazard motion, and they collide with each other. And the well-known laws of classical mechanics are applicable to the motion of these molecules. Okay, so we have to actually learn some assumptions of kinetic theory. So the assumptions on which the mechanical picture of a perfect gas is based, I'm going to just make it in point form for you, that all the gases are composed of molecules that we have seen in our previous slide itself. And the molecules of these gases are identical, they are rigid, and they're very small in size. Okay. So the first point is already mentioned in our previous page, that is they are all identical. Sorry. They are all identical. And they are rigid. Sorry, because I'm not so much familiar with this whiteboard, so my sometimes it's getting very okay. They are rigid, they are identical, and they are small in size. The next point is that these molecules are in random motion, and the velocities of these molecules are in all directions, and that ranges from 0 to infinite. So the first thing that you should keep in mind that it's an ideal concept. So the velocities must be ranging between 0 to infinite, and the velocity of a molecule increases with temperature. Okay, so this is a very important thing, that the velocity increases with temperature. Don't forget this. During the motion, the molecules collide against each other and with the walls of the container in which it is kept. So between two consecutive collisions, the molecule moves in a straight line. So this is very important, because let's picture out this. Okay, I'm just trying to give you a glimpse of all the assumptions in pictorial form. So suppose I have a container, and these are my gas molecules. Okay, and when they are in motion, they are colliding against each other, and it's a random motion. Okay, and between two successive collisions, what happens is that they move in straight line. Okay, the distance is called free path. I think you have heard this term before as well. This is called free path of the molecules, and the average distance is called the mean free path. Just this mean free path. Fine. The mean free path is independent it's dependent on pressure of the gas, and if the pressure is high, the mean free path is less, and vice versa. Okay. So one important point is there. I'm not moving to the next page, I'm just writing here, is that these molecules are perfect elastic spheres, and they exert negligible force of attraction or repulsion on one another, and also on the walls of the container. So Newtonian mechanics applies to these molecular collisions. Okay, so they obey Newtonian mechanics. So in a direct impact, the molecules begin to move in an opposite direction with the same velocity. Fine. The next very important point of this assumption is that the time during which a collision takes place is negligible. So the collision time is negligible. And it is instantaneous. So collision is actually instantaneous thing. Collision is instantaneous. Okay. The number of molecules per unit volume of the gas is very large and it remains constant. So on an average course of time, since the molecules are like geometrical mass points, the actual volume occupied by them is negligible compared to the total volume of the gas, that is of the container. Okay. So we have done the basic assumptions. Just go through them once before we move on to the next part. So the next very important thing that we're going to start is keeping in mind all the kinetic assumptions of the kinetic model will bring out the expression of pressure that is being exerted by a gas. And for that, we consider an ideal gas being enclosed in a container. So let us suppose a hollow cubical vessel of each side, maybe say L. Okay, each side the value is say L, with perfectly elastic walls containing very large number of molecules. I suppose say N number of molecules, and consider one of the molecules having velocity C1. So the velocity of that particular molecule, which I have considered that has C1 velocity, can be resolved into three rectangular components. So I can resolve this into three rectangular components like U1 and V1 and W1 parallel to the x-axis, y-axis and z-axis. Okay. Okay, I'm showing it in a pictorial form. Suppose what I do is this is my x-axis, this is my y-axis, and yeah, I just resolve this velocity C1 into three components along x, y, and z. So this is my x-axis, this is my y-axis, and this is my z-axis. And I've resolved this C into three components, U1, U2, U1, V1, and W1, such that I can write that C1 square is equal to U1 square plus V1 square plus W1 square. Okay, I consider this equation as 1. So what have I done? I have taken a hollow cubical vessel of site L, and this vessel has perfectly elastic whorls, and it has a large number of molecules, of which I have considered only one molecule having velocity C1. And this C1 can be resolved into three rectangular components, that is U1, V1, and W1 respectively along X, Y, and Z axis, and I get this very expression. Okay, now I consider the motion in the direction perpendicular to the face A. Okay, this face A I'm talking about. Okay, this part perpendicular to the face A. The molecule strikes the face A, and it again rebounds. So it strikes the face A with a velocity, say, U1. Okay, it strikes the face A with a velocity U1, and then it rebounds back with the same velocity but in the backward direction. And why? Because the collision is perfectly elastic. So if mass of the molecule, if I consider the mass of this molecule to be, say, m, okay, then the change in momentum that have taken place during this collision would be mu1 I'm finding out the change. So I'll take minus of mu1. Why? Because the direction has been reversed, is equal to 2mu1. I think you're able to follow. It is moving in this direction, and then it is rebounds back in the with the same velocity in the backward direction, hence the negative sign arrives. So the molecule now travels from A to A prime. Okay, so it strikes A prime and travels back to A again after covering a distance of how much? Yes, 2L. So it covers a distance of 2L. The time taken by the molecule to go to the other phase and then come back is how much? Can I take a new slide? Okay. So what did it say? The time that is the molecule is taking to go to the other phase and then come back is actually 2L by U1. Okay, fine. So the number of impacts I can find out from here, the number of impacts per second is actually 1 by 2L by U1. So that is equal to U1 by 2L. Okay. And the change of momentum produced in 1 second due to the impact of this molecule, or simply I can say in a very simple manner that the rate of change of momentum. Okay, so I can say that rate of change of momentum is actually 2mu1 into u1 by 2l. So that gives me mu1 square by l. Okay, are you following? Okay. If you have any queries, then just write it up in the chat box. Once I cover this part, I'll check all the questions of yours and I'll discuss. Okay. So according to Newton's second law of motion, we know that the rate of change of momentum is equal to the impressed force. So if F1 is the force, then I can write. So I can write that F1 is equal to mu1 square by L. Okay, it's very simple. Okay, similarly, the force due to another molecule having a velocity, say c2, and whose components considered to be as u2, v2, and w2 respectively, will be given as F2 is equal to mu2 square by L, and so on. Okay, so are you following? Okay, so the total force, I can now find out the total force F on face A. Okay, face A of that cube is equal to mu1 square by L plus mu2 square by L plus dot 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 mun square by L. Okay, is it clear? Okay, so just take common m by L, u1 square plus u2 square plus u3 square plus dot 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 plus un square. I don't know, I don't remember. I'm just giving the equation number as 3. Probably it will be 3, I guess. Okay, so we have found out the total force F on face A. Now from this we can find out the total pressure on face A. Okay, so how will we determine that? So we know from formula that it is pressure is force upon area. So we'll have M by LQ and U1 square plus U2 square plus dot 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 plus UN square. Okay, now tell me one thing. What is this LQ? LQ is actually V. So I can replace this LQ by V and write accordingly. Okay. So PA equal to M by V U1 square plus U2 square plus dot 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 plus UN square. Fine. Let this be 4. Similarly for phase B, okay, similarly I can write for phase B perpendicular to y-axis now. This was perpendicular to my x-axis. This should be perpendicular to my y-axis, and hence the pressure would be M by V. It would be V1 square plus V2 square plus dot 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 Vn square. Okay. So similarly for phase phase C, which is perpendicular to z-axis, we can write M by V W1 square plus W2 square plus dot 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 Wn square. Okay. So as the pressure of the gas is same in all directions, so we can write PA is equal to PB is equal to PC. So I can write say P, okay? Say I'm taking it as P, or I can write P is equal to 1/3 of PA plus PB plus PC. Are you following, students? Okay. So P is equal to 1/3 of PA plus PB plus PC. After we complete today, please practice this. Okay. So I'm just putting the values of respective PA, PB, and PC over here, and I get U1 square plus U2 square plus dot 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 UN square. Take that M by V common from all, and I'm writing it in a single line. I then have this part V1 square plus V2 square plus dot 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 Vn square. And I have another part that is W1 square plus W2 square plus dot 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 Wn square. Okay. So these 3 parts is for this portions. Now open the brackets and bring all the ones together, all the 2 coordinates together, and all the similarly. So I'm just doing this part. So 1/3 M by V. I'm taking this one, and this one together. So I get U1 square plus U2, sorry, V. I have to rub out that. Okay. So V1 square plus W1 square. Again, I have the next part as U2 square plus V2 square plus W2 square. And the third part I have is U3 square, sorry, UN. UN square plus Vn square plus Wn square. Okay, make over here a few dots because I'm not considering that 3, 4, 5 and all. I'm just taking 2, 2, 1, 2, 1, n. Okay. Now, these portions were actually which part? That C1, this was actually C1. Then this must be C2 and this must be Cn. So I can write 1/3 m by v into C1 square plus C2 square plus dot 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 Cn square. Sorry. Plus Cn square. Okay. Give this relation 5. Up till now it's okay? Fine. Now the C, capital C, or is called the root mean square velocity of the molecules, and it is equal to the square root of the mean of the squares of the velocities of various molecules. So I can write therefore C square is equal to C1 square plus C2 square plus dot 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 Cn square by n number of molecules, or nc square is equal to C1 square plus C2 square plus dot 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 plus Cn square. Okay. Substitute this value in equation number 5 and you'll get P is equal to 1/3 m n c square by v. Okay, you must have got this, right? Now, the total mass of the gas I can write as capital M. How? If I have said that each molecule I've taken, let its mass be M, and the total number of molecules is say N. So M into N gives me the total mass of the gas. So I can write over here like M by V, it will give me rho, that is the density of the gas. So I can rewrite this above expression as 1/3 rho C square. Okay, 1/3 rho C square. I haven't, no, I just skipped one steps. Okay, wait. I just show you. Yes, it would be M by V. When I replace this M by this, then it becomes M by V, and M by V means what? Density. So I have just skipped one line. Okay, so this. Now it's okay? Okay, so you have derived the relationship or the expression of pressure of a gas. Okay, so this is very important. It comes in exams very often.